Hey, welcome! Have you ever really stopped to wonder how a raw egg turns into, well, a cooked egg? Or how a shiny new nail gets all covered in rust over time? It's all because of chemical reactions. And today, we are going to decode the secret language of change, the fundamental rules that explain how pretty much everything in our universe transforms. So let me ask you a question. What on earth could possibly connect a carton of milk going sour in your fridge, a piece of iron rusting outside, and you cooking dinner tonight? I mean, they seem totally different, right? But believe it or not, they all share one huge fundamental secret. And the answer is they're all chemical reactions. That's it. In every single one of those examples, the stuff you started with is fundamentally changed into something brand new. So today, we're going to dig into exactly how and why this happens. Okay, first up, let's just take a moment to appreciate how surrounded we are by all this chemistry. Seriously, these reactions aren't just happening in some far-off science lab. They're happening in your kitchen, inside your own body, and all around you, every single second of every single day. I mean, just look at this list. The variety is kind of amazing when you think about it. Milk curdling, grapes fermenting to become wine, heck, even the simple act of breathing to power our bodies. In every single case, the very nature of what you started with is changed forever. So if these reactions are happening all the time, how do we actually spot one in the wild? Well, it's time to become a reaction spotter. Turns out, there are 4 key clues to look for that basically scream, hey, a chemical change is happening here. And this is the big question, right? It's what every scientist asks. How can we be sure? What's the actual observable proof that something new has been made? To figure that out, let's look at a really simple experiment. So, just imagine for a second we're in a lab. We've got a flask with some dilute sulfuric acid, and we're about to drop in a few little pieces of zinc metal. What happens next? Well, that's our evidence. And boom, almost instantly 2 things happen. First, you see fizzing. A whole stream of bubbles starts rising up from the zinc. That's a brand new gas being created. And second, if you were to touch the flask, you'd feel it's getting noticeably warm. So these observations, they become our checklist. If you ever see a change in state, like a liquid turning into a gas, or a change in color, or bubbles suddenly appearing, or a quick change in temperature, you can be pretty darn sure you're looking at a chemical reaction. Okay, so we can spot a reaction. That's cool. But how do scientists talk about them? How do they describe them accurately? To do that, we have to learn the language of chemistry. And that means moving from simple words to these really concise and powerful formulas. The first step is what we call a word equation. And it's exactly what it sounds like. On the left, you list your starting ingredients. We call those the reactants. Then you've got the arrow, which just means turns into, and on the right, you've got your final stuff, the products. Super simple, nice and clear. But, word equations can get a little long and clumsy. That's why chemists use symbols. Just compare these two. The chemical equation on the right is so much sleeker, it's universal, and it's packed with way more information. It's kind of like the difference between writing out the words 1 dozen and just writing the number 12. Now, this new symbolic language, it has rules. And there is one absolute, universal, unbreakable rule of grammar. It's a law that governs every single reaction in the entire universe. And it's all about keeping things in balance. And here it is, the law of conservation of mass. This is a cornerstone of all science. All it really means is that you can't create matter out of thin air, and you can't make it just disappear. In any reaction, every single atom has to be accounted for. So what does this big law mean for our equations? Well, it's actually a pretty simple instruction. The number of atoms you start with for each element has to be the exact same number of atoms you end with. They can get all shuffled around and rearranged into new molecules, sure, but they can't just vanish into thin air. Okay, let's put this to the test with our magnesium example. On the left side, the reactants, we have 1 magnesium atom. And on the right, the product, we also have 1. Great, we're good there. But, look at oxygen. We start with 2 atoms of oxygen, but we only have 1 on the right side. That's a huge problem. This equation is unbalanced. It's what we call a skeletal equation. And right now, it's breaking a fundamental law of the universe. We've got to fix it. Which brings us to our final and maybe most practical part of this explainer, a balancing act. We are now going to roll up our sleeves and go step by step through how to take one of these messy, unbalanced equations and make it actually follow the law. Okay, let's get to work. Our mission, should we choose to accept it, is to balance this reaction between iron and water. And as you can see, it's a bit of a mess right now. The numbers are all over the place. But don't worry, we can fix this. We're not just going to guess and hope for the best. Nope, we're going to use a clear, methodical process. First, we'll do a head count of all the atoms. Then, we'll tackle the elements one by one to get them balanced. And at the very end, we'll do a final check to make sure everything is perfect. Let's do it. All right, step 1. Let's do an atom count and see what we're dealing with. And right away, the table shows us the problem. We've got 1 iron atom going in, but 3 are coming out. 1 oxygen goes in, but 4 come out. Only hydrogen seems to be okay, for now, anyway. Let's start with the biggest problem first, that oxygen imbalance. We need 4 on the left to match the 4 on the right. Simple enough, we just put a big 4 in front of the H2O. Now our oxygens are balanced, 4 and 4. Perfect. But wait, see what happened? By fixing the oxygen, we accidentally created a new problem for hydrogen. We now have 4 times 2, so 8 hydrogens on the left, but still only 2 on the right. No big deal. To fix this, we just place a 4 in front of the H2 on the right side. And just like that, hydrogen is balanced again, 8 on each side. We are on the home stretch now. The only thing left is the iron, and this is the easy part. We have 3 on the right, so we just need 3 on the left. We pop a 3 in front of the Fe, and I think that should do it. And now, for the moment of truth, the final check. Let's look at the table. 3 iron on the left, 3 on the right. Check. 8 hydrogen on the left, 8 on the right. Check. 4 oxygen on the left, 4 on the right. Check. We have a perfectly balanced chemical equation that respects the law of conservation of mass. We did it. So remember this, what we just did wasn't just some clever math trick. It was a form of storytelling. Balancing an equation is how we write a true sentence about how our universe works. A sentence that confirms that nothing is ever really lost. It just gets rearranged. And that leaves us with one final, much bigger thought to chew on. If every single reaction, from a nail rusting to a star being born, is just a reshuffling of the same eternal atoms, if nothing is ever truly lost and only ever changed, what does that really mean for the world around us and for our tiny place in it?